So technology is not good. Okay, so anybody? So maybe I'll shorten it a little bit. Okay, I'm going to so I'm going to divide my vertices into two pieces. The ones that these all have 3 zeros and 1s. Now I'm going to add. So now I'm just going to add a 1 to each of these. Okay, that's 8 of the vertices in this 4-dimensional cube. So what are the other points? What other points? So I have all the points from the 3-dimensional cube, and I've added a green 1 to each of those points. So what are the 0-1 sequences that I don't have yet? Everything that ends in 0. Okay, so I'm going to draw the cube over again. I'm going to draw the cube over again. I'd like to do it in red. And I'm gonna put 1 1 1, 1 1 0, 1 0 1, and 0 1 1, and then 1 0 0, 0 1 0, 0 0 1, and then 0 0 0. It looks very similar to where we were a few minutes ago, except I want vectors of dimension 4. So here are my vectors of dimension 4, where I've added a 1. There's a 4th in the last component is a 1. So what should be in the last component of each of these? 0. Okay. By the way, none of the adjacencies in that red cube have changed. They are now dimension 4 vectors, and each of the dimension 4 vectors differ in exactly one component. Now there's one more thing. What about edges between this cube and this cube? So where does 1 1 1 1 go? Okay, so it's adjacent to this one. Is anybody else adjacent to 1 1 1 0? No. Okay. So what about 0 1 1 1? It's adjacent to 0 1 1 0. So this edge is there. And 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 this edge is there. So this is a very beautiful graph. This is a graph that's 4 regular on 16 vertices. It has some very nice structure. You can say a lot about cycle lengths. Okay, by the way, it turns out that there are no cycles of odd length. Okay, so there are no 3 cycles. There are no 5 cycles. There are no 7 cycles, and so forth. It's regular of degree 4, and it has a very nice structure. And if I wanted to now produce the cube of dimension 5, how would I label the vertices? I'd make another copy of this, and I would add a 1 to all of these, and a 0. I'd make another copy and add zeros, and then connect the 2 that are adjacent, that are different in exactly one component. I won't do that. Okay. These are called the hypercubes. I know we've talked about the 3-dimensional cube and the 4-dimensional cube. And if you want to look on page 46, there's some problems about Qn. Okay, so 46, number 9. So how many vertices are, let's go back, how many vertices are there in the three-dimensional cube? 8. How many in the four-dimensional cube?
16.
Okay, so let's instead of 8, how many vertices as a power of 2 are in the three-dimensional cube? As a power of 2 in the three-dimensional cube. 2 to the third. And in the four-dimensional cube? And in the fifth-dimensional cube? Okay, so the n-dimensional cube would have 2 to the n vertices. And now it says, so find the number of vertices in Qn. For each of 1, 2, 3, and 4, we've done 3 and 4. 1 and 2 are pretty simple. Okay, show that Qn is regular. You might want to look at that. You might also want to show that it's connected. Why would it be connected? Well, let's see. Let's just make a very quick argument. Once I show that this is connected, then I know that this is connected because I can get from any point in the black cube to any other point in the black cube, and I go from any point in the black cube to a point in the red cube. Okay, so I know the whole graph is connected. Doesn't matter what the dimension is. So you might want to think about how you would write that down. And then it asks the number of edges. Wow. 3 times. Well, here. Okay, so the three-dimensional cube, is regular of degree 3. The four-dimensional cube is regular of degree 4. The five-dimensional cube is regular of degree 5. Okay, so the k-dimensional cube would be regular of degree k. And how many vertices would be in the k-dimensional cube?
2 to the power of k.
2 to the power k.
Yeah.
2 to the k. So I have 2 to the k vertices of degree k. What am I saying? That's 2 to the k vertices of degree k, but that's not the number of edges. This is the sum. This would be the sum of the degrees, and so the sum of the degrees is. So it's twice the number of edges, or the number of edges. Sorry, I'm running out of ink. So this is the number of edges. And k is bad, but q sub k. Okay. Is that clear? It's regular of degree k. Okay. Why did I divide by 2? Why? Oh, no. Yeah, so each vertex has degree k, and there are 2 to the k of them. So I'm taking up the sum of the degrees of the vertices. The sum of the degrees of the vertices, this is, as soon as you hear sum, degrees, vertices, there are bells going off, and you're going twice the number of edges. Okay? So I got to divide by 2, so that we only have 1 times the number of edges is equal to the number of edges in the cube. Okay, question? Fun exercise. Figure out what the diameter is. Figure out what cycle lengths are in there. So you can play with that. Questions? Questions about this? Okay. So I want to jump for a moment. So how do I know? I'm erasing all this, so I hope it's okay. It's looking over there. Don't look over there. Okay. I'm going to give you a sequence of numbers. Let me pick a good one. By the way, I'm on page 81. Here's a sequence of numbers. Bless you. Here's the question. Is this the degree sequence of a graph? is maybe it's not a good answer. Okay, is this the degree sequence of a graph? I don't care what the graph is. I just want to know, is there a graph that has that sequence of degrees? By the way, let's just make sure, if I give you this degree sequence, and if I put commas in there, if I look at that degree sequence, do you think that's a degree sequence of a graph? Okay. Well, in fact, not only do we think so, we've exhibited one. Okay. Everybody sees there's 8 threes. Okay. What about this sequence? What? Because there's a what? Okay, so this is a sequence of 7 threes. Sounds like it should be the degree sequence of a graph, but in fact, the sum of the degrees needs to be what? Even. And not only even, the sum of the degrees needs to be even.
2 times the number of
and it has to
edges.
be twice the number of edges. That's why it's even. Okay? Well, if I take the sum of the degrees, 3 plus 3 plus 3 plus 3 plus 7 threes, we get 21. Then the number of edges in this graph would be 21 over 2 would be 10 and a half. We don't have half edges. Okay? So I know that can't be a degree sequence. Okay? Is that clear? I know this can't be a degree sequence. Okay, so let's on page 81. There's a bunch of numbers here. There's a bunch of x. So there's 12 numbers. Sorry, 12 sequences. And I started with number 11. I just jumped to number 11. Let's back up for a second. So these are sequences of integers. It's nice. They're sequences of non-negative integers. That's good because we know degrees can't be negative. So having sequences of non-negative integers is good. Okay? So I'm going to start with number I. Again, on page 81, is 0, 0, 0, 0 the degree sequence of a graph? Okay, so one more time. At the bottom of 80, which of the following sequences are graphic? So what would it take to show that a particular degree sequence is graphic? What would I have to do? Okay, so one thing is to find an example. Okay, so can you give me an example? How many vertices is this graph? I'm doing I. How many vertices does this graph have?
4.
And what does the degrees have to be?
0.
4 zeros. Can you give me a graph that has degree sequence 0, 0, 0, 0? That's it. This is a sequence. This is a graph with sequence 0, 0, 0, 0. Okay? Okay, so 2, II. We can vote. 2 is 1, 0, 0, 0. 1, 0, 0, 0. One more time. What can you tell me about the sum of the degrees? The sum of the degrees here is 1, but I know that the sum of the degrees must be even. Sum of the degrees must always be even. Is this a degree sequence of a graph? No. I?
Yes.
Okay. So we can check. It certainly has a even sum, 1 plus 1 plus 0 plus 0. And now the problem is going to become, now I have to be able to produce it for you. Okay, so I is not hard, correct? You can do 1, 1, 0, 0. What does that look like? Just appease me. Tell me what it looks like.
There's a address
A
with the
line
first
and
column.
two.
Okay, so
What is this?
here's a graph with degree sequence 1, 1, 0, 0. Okay? IV,
No.
1, 1, 1, 0, because
It's odd.
it's the sum of the degrees is odd. Okay? Oh, that's great. Okay, V, sorry, 1, 1, 1, 1.
Yes.
Yes, and now it's a matter you can produce it. You can't just say because the sum of the degrees is even. That's not enough. That's not enough. You now, it's not an if and only if statement. If the sum of the degrees are even, then there is a graph that attains that. We're going to need to know a little bit more. Okay, we'll get to some. Let's see, 2, 1, 1, VI. By the way, 1, 1, 1, 1.
Connect the later
Two edges. Okay. By the way, yours doesn't have to look like this. Just to be different, I'm going to put my 4 vertices like this. There's a graph that has degree sequence 1, 1, 1, 1. Okay. 2, 2, 0, 0. Sum is even. I want a graph.
Multigraph, okay?
No. Okay, so if I want a graph, 2, 2, 0, 0 would not be okay. Everybody understands the difference between graph and multigraph. Multigraph, I'm allowed multiple edges, and a graph, I'm not allowed multiple edges. So 2, 2, 0, 0 would be a multigraph, but it's not a graph. Okay? Here, this one, 2, 1, 1, 1, 1, 0. The first test you're doing is what? It's you're going to sum them up. 2 plus 1 plus 1 plus 1 is 5. So this can't be the degree sum. This can't be the degrees of a graph. But what about 2, 1, 1, 1, 1, 1? That was too many ones. 2, 1, 1, 1, 1. 2 and 4 ones. Let's see. 2, 1, 1, 1, 1. It meets all the good conditions. The sum of the degrees is even. That's good. So this graph should have, how many edges should this graph have? If there is such a graph, it should have how many edges? 3 edges. Can't be too many graphs on 3 edges, especially if you have one of degree 2. How many vertices are there? 5. And these have degree 1, degree 1. Okay. 3, 2, 2, 1, 1. Wow. Now it's just crazy. 3, 2, 2, 1, 1. The sum is odd. No chance. Okay? You're going to stop me if you. Okay, so 4, 3, 2, 1, 0. 4, 3, 2, 1, 0. Okay, so let's do our check. We add up the degrees. 0 plus 1 plus 2 plus 3 plus 4 is 10, which is even. So there should be we should be able to do this with a graph with how many edges? Degree sum is 10, so 5 edges. So 5 edges, 5 points. 5 edges, 5 vertices, but I want the degree sequence to be 4, 3, 2, 1, 0. Why? This is great. Okay, can you say that louder?
Because there's 5 vertices.
There's 5 vertices.
And there's a degree of 4.
Here's 5 vertices. And there's a vertex of degree 4. And it's a graph, not a multigraph. So if this vertex has degree 4, then the only vertices it could be adjacent to would be those 4 vertices. But then we look at the rest of the elements in this set, and we have a 0. Oh, wait a second. All of these vertices already have degree at least 1. Okay, so this is not the degree sequence of a graph. Okay, take a minute. 4, 3, 2, 2, 1. Tell me the steps you're going to take. Four, three, two, two, one.
Yeah.
Okay, so I got the 4. Now what?
So we need a 3.
We need a 3. So no. I'm not sure. Can we?
It's okay.
It's okay.
Yeah.
Okay, one more time. This is 4. This is 3. This is 2. This is 2. Oh, and this is 1. That's it. Okay. Okay. We're gonna. There are two. There are two theorems in this section about when a degree sequence is realizable as a graph. One is very numeric. If you look at the Erdős-Galai, so theorem 2.5.3, we have a non-increasing sequence. All of these have been non-increasing of non-negative integers. It's good we have non-negative integers because we don't want any degrees negative. So we have to meet we have to meet condition I, and then we have to meet condition II for each k from 1 to n. So that's a lot of conditions. So we'll come back to that. I want to look at theorem on page 83. I want to look at this is what's called the Hubble-Hashimi. Sorry, where is it? Oh, there it is. So Hubble-Hashimi, the algorithm is on page 84, and the theorem is. So I have a sequence. Of degrees, and for Hubble-Hashimi, it's very important that we put them in non-increasing order. Okay, non-increasing order. So I have D. Sticky blue. D1 greater than or equal to D2 greater than or equal to D3 greater than or equal to Dn. Okay. So we take this non-increasing sequence of integers. Then D is graphic if and only if a different sequence is graphic. Okay, and here's the sequence. So what I'm going to do is, ideally, this is the vertex of highest degree. Maybe he should be adjacent to the next D1 points. So this sequence, D1, D2, D3, Dn, is graphic if there's a graph with this degree sequence if D2 minus 1, D3 minus 1, D4 minus 1, watch me carefully, down to D sub D1 plus 1. Let's see. So this is the first one. This is the second one. This is the third one. This is the D1. This is the D sub 1. D sub 1 plus 1. Let me write that so you can read it. D sub D1 plus 1. So this is the next D1 degrees, and I'm going to reduce those all by 1. And then D sub D1 plus 2. And then everything else stays the same. D sub D1 1 plus 3, down to dn. Okay, one more time. This is graphic. This sequence is graphic. If, graphic means there's a graph, if I can take the largest degree and essentially put it adjacent to the next largest degree. By the way, this is not in necessarily in descending order. Now I could have really messed things up. D1 plus D sub D1 plus 1 could come somewhere over here. So we could mess this up. So let's actually do an example. It's an if and only if. So let's do 5 4 4 3 1 1. 5 4 4 3 1 1. And by the way, I'm looking at of course this is sorry, I'm going to change this because this is. We'll come back to that. Let's do 4 4 3 2 2 1. 4 4 3 2 2 1. The question is this a graphic sequence? Is there a graph that has exactly these degrees? And now what I'm going to do is I'm going to remove the 4 and reduce the next 4. So this becomes 3, this becomes 2, this becomes 1, this becomes 1, this becomes 1. Okay? So one more time, I'm going to reduce the next 4 by 1. I'm going to reduce the next 4 by 1. 4 goes down to 3, 3 goes down to 2, 2 goes down to 1, 2 goes down to 1, and 1 I just keep the rest. So one more time. So I'm going to, this guy, so what I'm saying is, if this is realizable, what Hashimi showed, and we'll actually go through the proof, what Hashimi showed was that the vertex of highest degree, there is a realization where the vertex of highest degree is adjacent to the next, in this case, 4 vertices of highest degree. Okay? So one more time. This is realizable if this is realizable. So 4 4 3 2 2 1 is realizable if 3 2 1 1 1 is realizable. Yes. Yes, we can. So 3 2 1 1 1 is realizable if, now you got to be careful, 1 0 0 1 is realizable. Now that becomes pretty simple, but if we had a longer degree sequence, we now would put this in ascending order. So I put the largest ones here. We would write this as 1 1 0 0. But do you know that this degree sequence realizable?
Yes.
Yeah. What in fact, what's a graph? What's a graph with degree sequence 1 0 0 1 look like? How many vertices?
4.
And the degrees are 1 0 0 and 1. So the graph must look like. Oh, there it is. Okay. So the graph must look like this. And now what I'm going to do is I'm going to work backwards. And now, or maybe forwards, depending on how you look at this. And now I'm going to build a graph that has degree sequence 3 2 1 1 1. So what did we do in reverse? This is going to be my point of degree 3. The blue point is going to be my vertex of degree 3. And it was adjacent to the highest 3 degrees. Now careful, the highest 3 degrees was, so it's adjacent to a vertex of degree 2, and a vertex of degree 1, and a vertex of degree 1. So I'm not going to go, this is not right. It needs to have degree 3. This is not right. Because this vertex of degree, now the degree sequence would be 3 2 2 1 0. 3 2 1 1 1. So one more time. Okay, I'm gonna join the 3 to, let's see, so here's my 1, 0, 0, 1, and the 3 has got to go, so the vertex of degree 3 has got to go to the next highest ones. So the first thing I'm going to do is I'm going to 1, 1, 0, 0. I'm going to order it for the highest degrees. So going backwards, we want the degree sequence to be the degree sequence to be 2, 1, 1, 1. So 2. So I have a vertex of degree 2, and then 1, 1, 1. 2, of course, a vertex of degree 3, and then a vertex of degree 2, and then 3 ones. Okay, going backwards again. Now I'm going to add a vertex of degree 4. And it's going to make a vertex of degree 4. So here's my last point. This is the last point I'm going to add. Let's try a red that writes. That's as close as I get. So now that's going to be a vertex of degree 4. And we want to put it adjacent to 3, 2, 1, 1. So we want to put it adjacent to 3, 2, and it doesn't matter which one ones. Doesn't matter. And now what's the degree sequence? Degree sequence is 4, 4, 3, 2, 2, 1. 4, 4, 3, 2, 2, 1. So this algorithm, called the Hubble-Hashimi algorithm, Hubble-Hashimi, I don't know why it's never an and, it's always a hyphen, Hubble-Hashimi. Okay, this algorithm will tell me, if you follow this through, whether a sequence is realizable or not. And in fact, once you say, yep, it's realizable, because I come to a point where it is realizable, then going backwards you can actually construct the graph. Okay, we're going to prove this. We're going to prove this on, what's today? Today's Tuesday. Thursday. We're going to prove that this is the case on Thursday. Okay, so what I'd like you to do is on page 87, we've got 2 minutes. Pick one of these. Determine if each of the following is graphic. I'm going to say for the moment, pick one of these and determine if it's graphic using the Hubble-Hashimi construction.
So, curious. Let's say we had another 13 numbers out.
Right.
So then we get down to that bottom line. It's 1, 0, 0, 1,
Mm-hmm. Yeah.
9, 8, 3, all kinds of things. Then you try it again, we're going to end up with a -1.
No. You always move the biggest. You got to put them in order.
Oh,
the
you
first
got to
thing
rearrange it.
You got to rearrange them.
After.
Right. Yes, exactly for that. So if you wanted to actually program it, that's how you would take the largest one, subtract 1, 1, 1, 1, 1, and then reorder. Do it again.
Cool.
Okay. Is this the first one?
Yes.
5, 5, 4, 3, 3, 2, 1.
That's not the first one. That is the third one.
The third one. 5, 5, 4, 3, 3. Okay, what's the first one?
So it's 5, 4, 3, 3, 2, 2, 1.
5, 4, 5, 4, 3, 3, 2.
我觉得那样那样才对。
By the way, before you even start on these, before you even start applying Hubble-Hashimi, the first thing you want to do is make sure that the sum of these numbers is what? That's real important, because every once in a while I'll try and trick you. And I'll give you a set of integers that aren't even, and then you're going to try and construct it, and you're going to get in all sorts of trouble. Okay, so here's what for Thursday. Today is Tuesday, right? For Thursday, I want you to be looking at the problems, the potential degree sequences in problem number 1 on page 87. Okay, the potential, and then we're going to prove Hubble Hashimi, and we'll do a couple more applications. Questions? Comments? You're drawing graphs until all of your paper, you're running out of paper, you have so many graphs. Okay, see you Thursday. You look suspicious.
Yeah, I was thinking about so if we just -1, should we just reorder it to make the largest as before?
Right. You always have to reorder it so the largest is at.
So what about the 1001? Should we put the last one?
So I'm going to reorder it to be 1100, and then the largest is adjacent to the next largest, so the sequence becomes 000. And you know this sequence exists. Okay, it's not very interesting, but it exists. Yeah. So you
always need to reorder it.
Yeah, that's right. Oh, so construct. Yeah. So that's we'll do that on. Remind me on Thursday.
Okay.
Yeah. I mean, so essentially you're going to follow this back. Okay. Okay. So you know this is real life. Okay. So we know. So we have this graph. And now you're going to come along with a vertex of degree 3. Okay, so I'm going to come in with a vertex of degree 3, and I want 1, 2, and 1, 1, 1. 1, 2, and 3, 1. So I want 1, 2, and 3, 1. 3, 1, 2, and then 1, 1, 1. Okay. And now the next one is going to be a 4. So I'm coming in with a vertex of degree 4. Okay. I need 1, 4. And 1, 4. I need 1, 3. So I need to join it to the vertex of degree 3. Sorry. Yeah. No, it doesn't matter. Yeah, but that's the only place that vertex of degree 2. And now I need a 2 and a 2. So a 2 and a 2. And now my degree sequence is 4, 4, 3, 2, 2, 1.
Okay.
Yeah, so it goes, I mean, ask on Thursday. It goes forwards and backwards. The process goes one way to say, yes, it's graphic, but in fact, using this sequence, now you can actually build the graph. Got it? Good. Okay. Oh, yeah.
And I have a question about the irregular number 9. Can we use the method like we make one?
Yeah.
We set this as constant and only one register is can be like 0, 1, 1, 0, 1. So there are
Bye-bye.
there are n numbers and they have n times like I'm not sure how to show the result is irregular. If the n is come from the
Okay, so what? Tell me which problem you're working on. Which problem?
number 9, 46, number 9.
Hold on. So let me make sure we got I'm on the same page. Okay, so so you want to know the degree. So find the number of vertices, VQN is the number of vertices in the n-dimensional cube.
I want to know how to show that.
Okay. All right. So this is. Okay. There's the label for one of the vertices.
Yeah.
Okay. So, and these are all zeros and ones. Okay. So now, these are all zeros and ones. I'm gonna use some notation. Okay. This means not. So if this was a 1, then this is a 0. If this is a 0, this is a 1, and everything else stays the same. Now look at these two vectors. How many places do they differ in? 1.
And there are n possible.
Yeah.
Okay, thank you.
Sorry, I didn't make that clear. Sorry.
No, it was just.
What class is in here now?
Applied regression analysis.
Oh, real math.